Welcome students. In this lecture we are going to study how to evaluate integrals using Parseval's identity pertaining to Fourier cosine transform. So before starting the problems, let us have a glimpse on the Fourier cosine transform definition. Fourier cosine transform for a function f of x is defined as fc of f of x is equal to root of 2 by pi 0 to infinity f of x cos sx dx, and the final output is denoted as fc of s. The Parseval's identity pertaining to Fourier cosine transform is this: integral 0 to infinity fc of s whole square ds is equal to integral 0 to infinity f of x the whole square dx. Now let us see how to evaluate some difficult integrals using these Parseval's identity and Fourier cosine transform definitions. Look at the first one. Evaluate the Fourier cosine transform of the following exponential signal x of t e power minus at into u of t for a time t greater than 0. So this is an exponential signal they have given. For this we need to evaluate Fourier cosine transform, and hence we have to apply Parseval's identity to evaluate a specific integral like this: integral 0 to infinity dt by a square plus t square the whole square. Actually, if you look at this integral, it is looking very complicated. Using our usual analytical method and other integration formulas, if we try to integrate this integral, it is going to be very difficult. But let us see how to use the Parseval's identity of Fourier cosine transform and easily how to get the answer for this integration. First, let us go to find the Fourier cosine transform of this given function. So, given function is x of t is e power minus at into u of t, which is the exponential signal given here. Actually, u of t denote the unit function, so which is equal to 1 for t greater than 0. So, we can rewrite this x of t as just e power minus at, and we can denote the function as f of t here. Just changing the name of x of t as f of t, since we need to use Fourier cosine transform. So we have here fc of a function f. Just to maintain the same notation, we are calling this x of t as f of t. This is the Parseval's identity. Okay, now first let us evaluate the Fourier cosine transform for this function f of t. This is the definition of Fourier cosine transform. Fc of a function f of t is root of 2 by pi 0 to infinity f of t cos st dt, and of course the final answer is fc of s. We have to evaluate this, where the function f of t now is e power minus at. See here, e power minus at. So substitute in the place of f of t, let us substitute e power minus at into cos st dt. Now when you look at this integration, we cannot use Bernoulli's law. Usually we use Bernoulli's law for integrations having two terms like this, but here we cannot use because both of the terms will keep on differentiating and integrating. So there will not be any end in the Bernoulli's formula. So we may have to use a different method here. So look at this integration formula, which is a basic integration formula. We have integral 0 to infinity e power minus ax into cosine. Whenever we can make use of this formula. So is it not of the same pattern here? Yes, we can compare this, and we can make use of this answer here. So here already one root of 2 by pi is sitting out into, see, comparing this and this, in the place of a here we have a, but in the place of b here we have s here, and the variable of integration is t instead of x. Here we have t, that's it. So a by a squared plus b squared. In the place of b here you have s. So a by a squared plus s squared. So this is the final answer of the Fourier cosine transform of this function, which we call as fc of s. So this is the function f of t, which is e power minus at, for which we found the Fourier cosine transform like this: root of 2 by pi a by a squared plus s squared. So this is the answer. Now look at the integral which we have to evaluate. See, this is the integral which we need to estimate. So look at this integration and look at this answer. See, look at the answer of FC of S and look at this integration. We have the same term here. Are we not having the same term? But in the denominator we have a square. So it tells us that we may have to square this term. So that is why we are coming to Parseval's identity. So we may have to use Parseval's identity here, since there is a necessity in the integration to square this term. So let us write the Parseval's identity. See, once you have decided that you have to use Parseval's identity, first just write the Parseval's identity and literally substitute the values of FC of S and F of T in both sides. You will get the answer. Okay, here in the place of FC of S, let us substitute this. So Parseval's identity says integral 0 to infinity FC of S whole squared ds equal to integral 0 to infinity F of T whole squared dt. Okay, in the place of FC of S, let us substitute. So this is FC of S, square this. So when you square this, you have like this. And F of T is e power minus at. And when you square e power minus at, we have e power minus 2at. So remember, e power minus at whole square is going to be e power minus 2at. So here you can see that e power minus at whole square is actually e power minus at into e power minus at, which is e power minus 2at. So the right side is e power minus 2at, and that you can easily integrate and get the answer. So this e power minus 2at, when we integrate, we have e power minus 2at divided by minus 2a. So divided by minus 2a, now we have to apply the limit from 0 to infinity. So the upper limit, in the place of t, you have to put infinity. So here you have e power minus infinity by minus 2a minus lower limit. In the place of t, we have to put 0. So e power 0 divided by minus 2a. So upper limit minus lower limit. Now you know the basic values of exponentials. E power minus infinity is 0 and e power 0 is 1. So when you substitute, this becomes 0 and this e power 0 is 1 minus minus plus. So the answer is 1 by 2a. So this is the answer for this right side integration. Now look at the left side integral here. So here you have 2a squared. This is a squared. 2a squared by pi is a constant. We can take out of the integral 0 to infinity. And here you have 1 by a square plus s square the whole square ds, which is equal to now the right side value we have got, just we shall substitute, equal to 1 by 2a. Now when you look at this, according to the question here, if you look at the question here, the variable of integration they are using t, but here we are having in terms of s. See, here we are having in terms of s. So just it's like changing the name of the variable. It's just name change. So the name of the variable s we are changing to the name t. So here you have dt a square plus t square the whole square is equal to this side 1 by 2a, and take this 2a square by pi to the other side. So it becomes pi by 2a square. So the final value is pi by 4a cube. So this is how we have to evaluate an integral using Parseval's identity. Now let us do one more problem. Evaluate the integral 0 to infinity dx by x squared plus 9 the whole square. So this is exactly the similar one compared to the previous problem. Here generally you have in terms of a. Here specifically you have a number. So let us see how to do this. First we have written what is Parseval's identity. And this is the Fourier cosine transform definition, the FC of S definition. And when you look at this, see here a squared you have, here you have 9. So if you compare these two terms, instead of a squared here, 9 is sitting. So the particular a which we have to select is 3. So we have to choose the function f of x as e power minus 3x. So remember, this particular integration we got by evaluating the Fourier cosine transform of e power minus at. So here, instead of a, here you may have to use 3. So that is why you are choosing the function e power minus 3x. So now let us evaluate the Fourier cosine transform of e power minus 3x, and this is the definition. Root of 2 by pi 0 to infinity f of x cos sx dx. So this is my f of x. And e power and cosine, whenever it comes, we have to use this formula. a by a square plus b square. So already root of 2 by pi is sitting out. A by, what do you have in the place of a? 3. So 3 by a square, 9 plus, in the place of b here you have s. So s square. So this is the final answer of FC of s. So this is my input, which is e power minus 3x, and this is my output, that is Fourier cosine transform answer. This is the answer I have got. These two we may have to substitute in the Parseval's identity. So as usual, let us do that. In the place of FC of s, substitute this answer. See here, FC of s square we have. So square this, and right side you have f of x square. So f of x is e power minus 3x, that you have to square. So e power minus 3x, when you square you have e power minus 6x. See, like this I have explained here. E power minus 3x, the whole square is actually e power minus 3x into e power minus 3x, which is e power minus 6x. And this is a very simple integration which we can integrate and get the answer. E power minus 6x, when you integrate e power minus 6x by minus 6, 0 to infinity. And apply the limit, upper limit, in the place of x you have to put infinity, minus lower limit, in the place of x you have to put 0. So upper limit minus lower limit. And as usual, e power minus infinity is 0, you know, e power 0 is 1. When you substitute that here, e power minus infinity is 0, so this is 0. And this is 1, so the answer is 1 by 6. And this is of course the value of the right side term. See, this integration answer is 1 by 6. And what do we have in the left side? See here, this is the left side we have. So taking this 3 square, 9 into 2, 18 by pi out, 0 to infinity, 1 by s square plus 9 the whole square ds equal to the right side value is 1 by 6. So look at this integration and compare with the question. Here you have integral dx by x square plus 9 the whole square. Here you have ds by s square plus 9 the whole square. Same term has come, just we need to change the name of the variable as x. So changing the variable s to x. See here, we have dx divided by x square plus 9 the whole square equal to, taking this 18 by pi to the right side, 1 by 6 into pi by 18. So the final answer is pi by 108. So using Parseval's identity, we have learned how to evaluate these kind of integrals. So in the first problem, we saw a general integral in terms of a, and in the second problem, specifically for a number, we have seen how to evaluate such integrals. So using these concepts, try out these problems. Thank you.